Hi, and thanks for dropping in on these clips of the Sydney Basin, where I'd like to share with you the story into how the Sydney Basin works from a natural perspective, looking at a lot of the natural elements and the natural processes like fire and erosion, the eucalypts, the sandstone flora, the Watermatta shales, the Hawkesbury sandstone that is such a dominant and signature rock of this particular region, and also the interrelationships that we as people have with the natural environment, like some of the national parks and how we engage with those national parks from a recreational perspective, from a leisure perspective, from an aesthetic perspective. During the recent COVID, national parks provided such an important part of our rest and recreation to give us a bit of a break from what was going on in the cities. And of course, our natural areas are so important for conservation of our natural and cultural heritage. And what I like to do is I swing out to part of the Sydney Basin, which is behind me here, and that's looking out to the southwest, is to acknowledge the Gadigal and Wongal peoples on whose lands I'm currently filming. And we'll be travelling to other areas, to other Aboriginal nations like the Dharawal and the Darug. And I'd like to acknowledge those folk as well, and the traditional lands for which they have had such a long and continuous and intimate connection and relationship. And hopefully through these clips you'll develop your own relationship and your own intimacy with these particular natural areas. But for now, we're going to go deep into history. Deep, 4.5 billion years. To find out how the Earth actually evolved and what was some of those key periods along that evolutionary story. It's going to be a fascinating journey. We're going to condense about 4.5 billion years into just a few minutes. So I'm looking forward to sharing that story and looking forward to sharing more clips with you over the coming weeks. That's me, right down the end of this white line in that blue circle. And I'm going to use this white line to represent the 4.5 billion year history of the Earth. I'll be starting at 4.5 billion years and travelling to where you are in the present day. We flip to an overhead view to have a look at where we'll be stopping along the way. So our first stop will be at 3.3 billion, second stop at 2.2, then the home stretch starting at around the 1.1 billion years and through to the present day. And to give you an idea of just how long that timescale is, if we were to put the evolution of the human species on this timescale, it wouldn't even be the width of a blade of grass. Earth, 4.5 billion years ago, and it is starting to form from all the loose material that was created by the formation of our solar system. Bit by bit, those materials would come together to form our current day Earth. Earth's surface at the time was chaos. There were oceans of lava and molten rock, endless landscapes of volcanic activity, and meteorites pelting down from space as part of what's called the Great Bombardment. And the atmosphere was a toxic mix of poisonous and noxious gases. At around the same time, a large Mars-sized object collided with the Earth and sent a mass of material back out into space. That material would form our moon, which at the time was some 10 times closer to the Earth than it is today, and the Earth itself was spinning at a much faster rate, such that a day on Earth back then would have been 6 hours long. On to our next stop, which is in about a billion years, at around the 3.3 billion year mark. Now, to give you an idea of just how long that is, let's imagine we could go on some kind of spacecraft that accelerated time. Now, we accelerated time by 1,000 times, it would still take us a million years. Let's say we accelerated time by 10,000 times. It would still take us 100,000 years. Let's say we accelerated time by 100,000 times. It would still take us 10,000 years to get there. I think you get the idea. It's a long period of time that we're talking when we're talking the evolution of the Earth. By 3.3 billion years ago, the activity associated with the formation of the Earth had settled down somewhat. There is evidence that the Earth's surface had cooled, continental plates had formed, and that plate tectonics was underway. That's when areas of the Earth move around, bumping and sliding and pushing over each other. Beyond the Earth, our young sun, which was formed around the same time as the Earth, was steadily growing stronger and was about 3/4 of the strength of what it is today. There is also evidence that life had made an appearance in the form of single unicellular organisms, and today these are represented by fossils and living organisms called stromatolites, which are found throughout different parts of the world, including Western Australia. And in Western Australia, there is also evidence of the oldest mineral zircon, which has been dated to 4.4 billion years ago. And that puts it close to when the Earth was formed and during that chaotic period that we talked about before. Time to say goodbye to 3.3 billion years ago as we head to the halfway point, which is around 2.2 billion years ago. Now, the reason I'm on my bike is because I want to get there in a bit of a hurry, because there's been some exciting events that I'd like to share with you. And the first of those is the evolution of eukaryotic cells. And these eukaryotic cells were the forerunner of complex life, such as plants and animals, including ourselves. There was also an attempt for life to establish itself on land. Didn't quite make a big go of it. It was, I think, more slime. That's about the extent of it. But within the aquatic environments, life was really getting a move on. And leading this change was Cyanobacteria, an organism which was the first to start using the sun and the process of photosynthesis to produce their own energy, releasing oxygen as a byproduct. These days, Cyanobacteria is often known as blue-green algae, coming in the form of algal blooms. But scientists and researchers have been busy researching the potential of Cyanobacteria to reduce carbon dioxide levels and improve soil health in agricultural areas. It turns out it's one very important organism. Back around 2.2 billion years ago, as Cyanobacteria were doing its thing, the oceans were a green colour due to the dissolved iron from underwater volcanic activity. And these increasing levels of oxygen took a liking to this dissolved iron, leading to characteristic sedimentary rocks called banded iron formations. To use an analogy, it's the same reason your blood is red, because of that interaction between iron and oxygen. Within the aquatic environment, the increasing levels of oxygen reached a tipping point and started to leach out or dissolve out into the atmosphere. And for the first time in the Earth story, there were rising levels of free oxygen in the atmosphere. And within the atmosphere, oxygen found a new mate to bond with, methane, with carbon dioxide being the byproduct. Both methane and carbon dioxide are two potent greenhouse gases. And so with the level of methane being reduced by its reaction with oxygen and the levels of CO2 being reduced by photosynthesis, one commonly held theory is that this led to temperatures on Earth cooling to the point where the Earth became what is often referred to as a snowball Earth. Although some people call it snow sludge Earth. Regardless, it was cold. There were ice sheets, there were glaciers, there were ice flows from the poles up towards the equator. The Earth was a very cold place and remained so for hundreds of millions of years. Let's flip to our overhead view to see where we've been and where we're going. We started at 4.5 billion years with our first stop at 3.3 billion, then 2.2, and now we're at the 1.1 billion year mark. The last billion years is sometimes referred to as the boring or barren billion because it was a billion years in which not that much was happening. Volcanoes and earthquakes were reasonably quiet, climate wasn't flipping between warm and cold extremes, and biological evolution wasn't evolving. But the next billion years were to be the opposite, as life radiated with a diversity of form, shape and structure. It went from being primarily aquatic based to also colonising land and air. It went from small, singular and multicellular organisms to huge animals like the extinct Brontosaurus and current day blue whale, and to plants such as the tallest hardwood in the world, the Tasmanian swamp gum or mountain ash. And I thought it best to share this amazing journey through a short clip. Look forward to seeing you on the other side. That was quite a journey, 4.5 billion years in just a few minutes. And it just gives you a sense of how much has happened during the evolution of the Earth, just what kind of timescale we're looking at. And one of those is obviously the formation of the Sydney Basin, because that's what we're looking at with these clips. So to give you an idea of where that fits in to that timescale of the Earth's evolution, let's imagine that the Earth 4.5 billion years ago started at these fingertips, and the present day is these fingertips. Well, the Sydney Basin that we're going to be looking at and exploring and finding out more about would have formed around my wrist. So we're pretty much looking at a time span that would cover that palm of my left hand.